Okay, thank you. All right, so when they asked me to give this talk, I asked them if they wanted a research-style seminar on the research I was doing or on a more popular subject. So they said research, and so that's what I'm doing. However, I understand that the audience is undergraduates and maybe graduate students. So I'm going to go a little slower. I may not go through all the slides, but let's see. Let's see how we do. Let me just move my clock so I can see it. Okay, got it. So as I said, this is focused on the research that I do, not on the instrumental stuff, but on the astrophysics research that I do. Now, what I work on is the diffuse ultraviolet background. So if we go back to the historical context, this started as light of the night sky. And I'm showing this because it's interesting historically to show how the field has developed. When it started in the 50s, remember this was the dawn of the space age, and the focus was on international cooperation for atmospheric observations. So this was the time of the Cold War, but the hope was always that astronomy, space, science would bring all nations together into a community. And so this was, I think the International Geophysics year was 1957 when Sputnik launched, and so when we talked about light of the night sky, largely what was discussed was the atmospheric light from our own atmosphere. Now, as the field developed, they started to the space-based observations came in, and plus the atmospheric community moved over into space physics and geophysics, leaving this particular area for astronomy. And so so now it's largely astronomy. Now, what I'm talking about is the diffuse sky. And when I say the diffuse sky, that's not stars. For everyone else, the diffuse sky is part of the background. It's a contaminating source. For me, because I look at the extended background, I look at the sky and I throw away all the stars. For me, the stars are the background. The wavelength range of this sky background, it's actually a continuum. Although I'm interested largely in the ultraviolet sky background, it's a continuum that goes all the way from the gamma rays up to the long wavelength radio, including the cosmic sky background, the 3-degree background, and so on. But I'll focus largely on the UV part. Now, when I talk about the UV, I'm talking about wavelengths between 10 nanometers and about 320 nanometers. Now, the shortest part of this, 10 nanometers to 91 nanometers, is the extreme ultraviolet. And this is below the Lyman edge of hydrogen. That is, hydrogen is ionized at wavelengths shorter than 91 nanometers. There's so much hydrogen in interstellar space that any shorter wavelength light will ionize the hydrogen and we won't see it. So basically, the EUV, we just can't see anything. Then we go to the FUV, and this is the far ultraviolet. Now, these names change a little depending on who's talking about it and what the context is. But we can talk about the FUV as between 91 nanometers and 120 nanometers. And this is, again, technology related, because 91 nanometers, as I said, it's where the hydrogen cutoff is. So shortward of 91 nanometers, you won't get any light. And then 120 nanometers is where that intense Lyman alpha line is. That is the transition line from n equals 2 to n equals 1. Hydrogen is the most common substance everywhere, including in our atmosphere, our outer atmosphere. And so the n equals 2 to n equals 1 line is so strong that it'll dominate anything that we see. It also works out that we have we have long pass filters. We can cut off things shorter than some wavelength, but it's hard to cut off anything at Lyman alpha. So again, this is technology related, and we can define the NUV to be 120 nanometers to about 320 nanometers. Now, 300 nanometers or so, the sun is a cool star, temperature of 5,000 or 6,000 degrees. And so longward of about 300, 320 nanometers, the sun becomes so bright that we can't really see anything from of the diffuse sky background. The diffuse sky background is faint. And so really, when we want to look at the UV part, the UV part of the diffuse sky background is where the contribution from the sun is least and where the sky is brightest. Now, the units that we use are photons per centimeter squared per second per steradian per angstrom. So I don't want you to worry too much about all the units, but the point is that because we have energetic photons, we actually count every single photon. So our detectors are typically photon counting detectors. Now, so all of that is just definitions. So what do we really see? Well, this is from an experiment that we had on the space shuttle a long time ago, back in 87. And we had two spectrographs on looking up at the sky. So what you can see, I don't know if you can see my mouse, but it doesn't really matter. This a bright line to the left of this image is what I was talking about, the Lyman alpha line. That is the line, the light from terrestrial hydrogen that's excited by photons from the sun and then re-emits light in that first excited state, n equals 2 to n equals 1. If you remember the Bohr atom, you have n equals 1 is the ground state, n equals 2 is the first excited state, and so on. So this is photons from the first excited state to the ground state, and it's bright. Now what you see in this image is wavelength from left to right. So this bright Lyman line is at 120 nanometers, and over on the right edge, you have 320 nanometers. And then from bottom to top is increasing time. So the bottom part of this image is where the space shuttle just enters into darkness. And then the top part is where the space shuttle just leaves darkness. So as you probably know, the space shuttle used to orbit in low Earth orbit. And so each orbit took about 90 minutes. And so this is about 25 minutes of observation time. It leaves it leaves twilight, and then it re-enters dawn. So these lines here are oxygen lines. At nighttime, there's no emission from any of these lines except for Lyman alpha. And these bright lines here are nitric oxide. Now, this you see these lines here. These lines are stars that the space shuttle passes over as we scan the sky. But then most of what you see is diffuse sky background. And so this is what I study, the diffuse sky background in the ultraviolet. You can see that it's brighter as you go to longer wavelengths, and that's because of zodiacal light. That is, light from the sun that's scattered by interplanetary dust. Now, as I told you, the sun is a cool star, temperature of 5,000 degrees or so. So the sun has no emission below about 2000 angstroms. So now if I want to look at the sky and I want to avoid atmospheric light, I have to go outside of the Earth's atmosphere. If I want to avoid zodiacal light, I have to either go into the far ultraviolet, that is the left side of this plot, or I have to go entirely out of the solar system. So the earliest observations were rocket flights, and these were in the late 60s, and they discovered a diffuse UV background, but they were always difficult, and the observations were uncertain. So later experiments, Voyager, the two Voyager spacecraft launched in 1977 to explore the outer planets, but the outer planets were only a small part of the length of the mission. And so during their cruise phase, when they were between planetary encounters and after planetary encounters, we managed to use Voyager to observe the diffuse sky. And then I'll also tell you about FUSE data. That is another spacecraft that was launched to observe stars. All right. Now, most of the data that I've used comes from the GALEX spacecraft. And this is the Galaxy Evolution Explorer, and this was launched by a Pegasus from an L-1011 specially modified airplane. And so this airplane, what it did was it took the Pegasus launcher up to whatever altitude, 12 kilometers or 15 kilometers. And then the L-1011 dropped the Pegasus. The Pegasus ignited and went up and inserted the satellite into orbit. So this was a way to save the fuel to get it up to 12 or 15 kilometers. Most satellites these days are not launched that way. They're actually launched from regular rockets. So what GALEX did was it took the first survey of the sky in the ultraviolet, and it did this with two imagers: the far ultraviolet, which worked from 120 to 1500 nanometers, and the NUV, the near ultraviolet, which worked from about 1800 to 300 nanometers. And this is what I mean when I say that it's what you call FUV and NUV is context driven. For instruments, it's because GALEX had two imagers on board, it was one was shorter wavelength and the other was longer wavelength. So it was so they called it near and far and near ultraviolet. Now, what this is an exposure map of the sky. And so this is the far ultraviolet and the near ultraviolet. As I said, the far ultraviolet is between 130 and 180 nanometers. And the near ultraviolet is between 180 and about 300 nanometers. And this is an exposure map of the sky. You'll see several things. The first is that you see that the galactic plane was not observed. Now, the reason for this is because they were worried about the bright stars in the plane of the galaxy damaging the instrument detectors. As the FUV has fewer observations than the NUV because their power supply failed about 5 years into the mission. Near the end of the mission, they said, okay, now we're near the end of the mission. We don't care so much about lifetime. So now we'll allow the spacecraft to start observing at at lower latitudes, closer to the galactic plane. And so you see that there are parts of the galactic plane that are filled in by the NUV. You see a few regions that have a lot of observations. These are these darker shaded regions. And those are darker because there was some interesting part of the sky. Maybe places like the Virgo cluster of galaxies, the Coma cluster of galaxies, things like that. The places that were of great interest for one reason or another. If I look at an individual GALEX observation, now here again on the left-hand side is the FUV and the right-hand side is the near UV. And so what you see is that there are a few stars. Here's a star in the FUV, here's another star, maybe there's a star here and a star here. In the NUV, there's a few more stars. Now this field of view here is about 1 degree in size, that is the size of the full moon. And if I were to look at that same field of view in the optical, I would see lots of stars. So here's one advantage of going into the ultraviolet. You just don't see that many stars. You just see how dark it is. There are just no stars there. Most of the rest of the field is what I look at. It's the diffuse sky background, the diffuse galactic light. And in the NUV, this is what is in the FUV. It looks like it's a little bit brighter. And that's because the NUV has this zodiacal light that I was telling you about, the light scattered back to us from interplanetary dust. Now, the way the GALEX observations happened is that they took fields of the sky like this. And these are all, these images are all available on the Space Telescope data server. So that's one of the basic sites for ultraviolet astronomy, the Space Telescope website. And so all of the GALEX data are available from there. And that's a total of almost 45,000 observations. Now, the way a GALEX observation worked is that, as I told you, the GALEX was in near Earth, is in low Earth orbit. And so each observation takes about, or each orbit takes about 90 minutes. Out of those 90 minutes, you get about 20 minutes of observation. So if you want to take very long observations, longer than 20 minutes, you have to stack observations. You take an observation in one orbit, and then you go back to that same area of the sky in the next orbit, and so on. And so each of these are called visits. And so there were 44,000, almost 45,000 observations, but these observations were broken up into more than 100,000 visits. Now, this is important for my purposes because all of these data are available at Space Telescope, but the standard processed data adds together all the visits to give you one file for each target in the sky. And they try to subtract the background and all that. So, but I want the background. I don't want what they subtract. So in order to, I have to go back to the raw data. Now, as it turned out, I was actually visiting Space Telescope at the time. And so I asked them to give me the data on a disk drive. They gave me the data. And then as soon as I got back home, I found that the drive had been corrupted. So I had to re-download all the data. So I wrote to them and apologized. I said, look, I'm downloading a couple of terabytes of data. And they said, oh, don't worry about it. People download that much data all the time. We won't even notice. And this is one of the things that I wanted to stress in my talk, that these data are all publicly available. And so even though I was not one of the participants in the GALEX mission, we actually had a competing experiment. Even though I was not one of the participants, the data are still available. And so I can use the data as I like. And what's more, because I know the people in the GALEX mission, they helped me understand various instrumental factors there. So the point is that all of these data are available, and anyone can download it and use them as they want. Okay, so I downloaded these data. They're about a couple of terabytes of data, and I reprocessed them in my own way for my own purposes, because what I'm interested in is the diffuse galactic light. And so the first thing I did was I took the visits. I didn't take the observations. I took each visit. So this was 100 plus thousand visits. Each visit, each image is a 3,000 by 3,000 pixel image. So you can imagine how much data that is. I blanked out all the stars. I told you I don't like stars. The stars are my noise. And so I blanked out all the stars. But in actuality, the stars only contribute a few, 10% in the far ultraviolet and 30% in the near ultraviolet. So most of what I see is actually what I want to see, the diffuse galactic light. And then I had to subtract the zodiacal light and the air glow from each of my visits. Okay. So I won't go into much detail on these plots, but the first thing to do was that I had to subtract the air glow, because what I'm interested in is the diffuse galactic light, and so that's the light from the galaxy. In order to observe the light from the galaxy, I have to subtract whatever I see from the Earth, and then I have to subtract whatever I see from the solar system. And then I have to subtract whatever stars I see. So as an aside, you can imagine that the cosmic microwave background measurements, they have an even harder job, because they're trying to measure the radiation from the universe. So they have to subtract the light from our atmosphere, then the light from the solar system, and they have a problem because there's solar system dust everywhere, and the dust is heated to a temperature of about 60 degrees, and that happens to radiate in much of the emission it happens to radiate significantly in the wavelengths they want to observe. And then they have to worry about the galaxy, and the galaxy is filled with this dust at a temperature of 20 to 30 degrees Kelvin, and that again competes with the cosmic background. So in order to extract all of these, it's not enough to just understand what you're trying to extract. You also have to understand everything that comes in front. And so the first thing I wanted to do was I wanted to subtract the air glow. And so I did this from another of their data products, the total event count. Basically, all it did is it just counted the total number of counts in each per second. And unfortunately, and this is some of the problems that you get into when you do data analysis, what I needed to know was I needed to know the local time, the time on the spacecraft. But all they gave me was the GMT, the time, universal time. And so I had to convert UT of the observation into spacecraft time. And the only way you can do that is if you know the orbit of the spacecraft. And then the only way you can get that is if you use these things called two-line elements. And so as it turns out, the two-line elements are archived on a website. So I had to register on that website, download all those two-line elements, and then use another program to convert spacecraft time into, or UT into spacecraft time. And when I finally did that, I found that the air glow was very tightly correlated with the time from midnight. That is, it was least at midnight. And then as you get closer to twilight or to dawn, the amount of air glow increased. So I calculated this function, and then based on my observation, I subtracted the air glow. Now the next thing I have to worry about is zodiacal light, which is light from the sun scattered from dust in the solar system. And this is only there in the NUV, it's not there in the FUV. And because it's related to the solar system, everything in the solar system is related to ecliptic latitude. That is, all the planets are in the ecliptic plane, and most of the dust is in the ecliptic plane. So as you get further from the ecliptic plane, your zodiacal light goes down. And so when I plotted all of these data, I found a strong relation with ecliptic latitude. And so again, I found a formula so that I could subtract the ecliptic latitude. So now this gave me the GALEX data. So before I get to the GALEX data, let me go back to the data I showed you earlier, or to the spacecraft I talked about earlier, Voyager and Fuse. Now, as I told you, these were both taking serendipitous observations of the sky. There were a lot of observations, but observations of selected areas. Many of those observations were taken for other reasons. They were not taken to observe the diffuse sky background, but because the sky is dark there anyway, I managed to get an observation of the sky background. And so this is what the sky looks like, shortward of 120 nanometers. This is from 900 to 1200 nanometers. And you can see there's not actually that much data. These are all pointed observations. Here you see the the SCO-OF association. It's basically a bunch of bright stars, and the light from them is being scattered from interstellar dust. Here is the Large Magellanic Cloud, and then otherwise you have data scattered throughout the galaxy. So just remember this and compare it with these data, which are the all-sky data from the two GALEX instruments, the FUV and the NUV. So when I took all those 100,000 visits, I subtracted the airglow and the zodiacal light from each one of those observations. And then I added them all together to make a map of the sky. So the black region in the center is where the GALEX spacecraft did not observe. And I showed you that in the exposure time mapper before. But then the white is the brightest areas, and then these darker shaded regions are the darker areas. And so what you see is that the sky is brightest towards the galactic plane. So no surprise there. Most of what you see is light scattered from interstellar dust. And so that light scattered from interstellar dust, you have to have bright stars and you have to have dust. Where do you have bright stars? In the plane of the galaxy. Where do you have dust? In the plane of the galaxy. So naturally enough, the brightest parts of the galaxy are those is the plane of the galaxy. And this, in fact, you will find to be true of almost anything to do with the galaxy. It's brightest near the plane, and it's faintest as you go towards the poles. So that I certainly see. But I also see a few bright regions. So if you look at this bright region, I guess about halfway between the center and the top, on the right-hand side of the plot, that's Spica. Spica is one of the brightest stars in the sky. And I see light from Spica that's scattered from dust around Spica. So this map lets me see both the broad scale and the narrow scale features of this ultraviolet background. So now let me try to motivate this a little. Why am I interested in this? Why do I care about the ultraviolet background at all? Now, this is something that I've always found a difficult question to answer, because we're doing basic science. And when we do basic science, we're trying to understand how the universe works. Whether it's biology or chemistry or doing vaccine research, we're basically trying to understand how the universe works. And so that means that we have to understand every aspect of it. So at the most basic level, why do we want to understand the diffuse ultraviolet sky background? Well, because it's there. What's causing it? We want to understand why it's there, what's causing it, what effects it has, what it tells us about everything else. But the foundational reason is because it's there. It's there, and we want to know more about it. You probably want to see that. You've probably seen that that meme about why explorers want to climb a mountain. Well, because it's there. So why do we want to know about the sky background? Because it's there. It's the sky background. If we don't know about it, there's a hole in our understanding of the universe. Now, I can try to justify it on other grounds also. So what you're really looking at here, I've already subtracted the foreground emission. I've subtracted the air glow and the zodiacal light. So what I'm looking at is the galactic light and the extragalactic light. So when I look near the galactic plane, what I'm looking at is mostly galactic light. Why am I looking at mostly galactic light? Because that's where the galactic light is brightest. The bright stars, all the dust. So that's where the galactic light is brightest. As I go to the poles, now there's very little dust at the poles. As I look straight up out of the galaxy, there's just not much dust there. And there's not many stars there. Most of the stars are concentrated towards the galactic plane. So as I look up at the poles, what I'll start to see is the extragalactic light. Now, what comprises the extragalactic light? Well, that's the light of far distant galaxies. These galaxies have been, they cover everything in space. And so I will see them as a background source to my, when I look out towards the poles of the galaxy. So these two maps tell me everything about, or tell me many things about the interstellar dust, because that's what gives rise to the galactic light. It's the starlight scattered from the interstellar dust. It tells me about the extragalactic radiation. So when I find the extragalactic radiation, that allows me to put models or to put constraints on other galaxies, on quasars. Tells me how much they are, how they evolve, and all this stuff. So when I do look at the extragalactic, or when I try to understand what I'm seeing here, my own focus is the dust. I'm interested in the interstellar dust. And so this tells me about the properties of the interstellar dust. But it has ramifications that spread throughout all of astronomy. And this is true no matter what you do. You may study lithium stars, you may study exoplanets, you can study galaxies, you can study quasars, but you can't do any single thing without having a broad overview of all of astronomy and how results in other fields of astronomy might apply to your own field. All right, so now let me tell you a little bit about the modeling part, because now in the old days, the sociology, this is part of the sociology of science. Maybe 50 years ago, people could just do observations. So I would observe something and I would say, look, this is what I observed. Now it's up to you to figure it out. But astronomy has evolved since then. It used to be that there were two fields, astronomy and astrophysics. But now really everything is just is the same. Whether you do astronomy or whether you do astrophysics, you have to not just observe things, but you also have to have at least some explanation of what you observe. So what I did was I created a model for at least the galactic dust scattering. In principle, this is pretty easy. I'm looking in the ultraviolet. When I look in the ultraviolet, there are not very many stars. There's maybe at most there's a couple of thousand stars that contribute to this diffuse sky background. So I know where those stars are. These are O and B stars, and I know where they are. So it's easy for me to take those stars and put each of them into a spot in the galaxy. So I've divided the galaxy into a three-dimensional box, and I put stars at their different cells in those boxes. I've actually used the Hipparcos catalog. Doesn't matter. I could have used Gaia or anything else, but I used Hipparcos, and that has more than enough stars for me. The stars are all of a given. If I know the spectral type of the star, then basically I know what its stellar spectrum looks like. This is the essence of the Hertzsprung-Russell diagram. Once I know the temperature of the star, I know the spectrum of the star. So I use model spectra for the star. And then the tough part for me is to assume the dust distribution. So this, again, there's various models for the dust distribution. I've used one from Greg Green, who was based it on Pan-STARRS data. But it doesn't really matter. So there's a dust distribution. And then I use some physical model for the scattering from the dust. So I use a reflectivity from the dust and albedo, and I have some phase function for whether it scatters in front or scatters off to the side. Again, these are all details. You put them in your model and just work things out. Now, the next part of what I do, so that part is pretty straightforward. I take the galaxy, divide it into boxes, and fill all those boxes with stars and dust. And then what I do is the actual calculation of the scattering. So the thing is that any given star will put off 10 to the, I used to know the number offhand, but maybe 10 to the 50 photons a second. So there's no way I can actually calculate that. And it's also not it's not solvable analytically, because I have random geometries. So my stars are in random places in there. There's no spherical symmetry or anything. So the easiest way to do this is through a Monte Carlo procedure. And this, again, you find in astronomy and in many other fields of science. If you don't actually know many of the details, the easiest thing to do is to do a Monte Carlo procedure, because that will let you use random numbers, and you use within a fairly reasonable time, you will get a good picture of the sky. So Monte Carlo procedure, you select a star at random, you emit a photon in a random direction, stop it after some random optical depth, and then see what you're left with at the end. All right. So I won't go into the details of that just because of lack of time, but I'll just tell you a few of the interesting results. So it turns out that, as I told you, in the UV, there are very few bright stars. And you saw that in the GALEX data. In the FUV image, there was only one star that you could see. And those are not bright stars. The FUV is sensitive down to about 20th magnitude. So that would have been a 15, 16 magnitude star. NUV is sensitive, had maybe 5 stars down to that level. So not very many stars. And it turns out that with 1,000 stars, you'll get 80% of the sky background. So that's all you really need. 90%. So no, yeah, 85, 90%. So with 1,000 stars, you get about 85 to 90% of the sky background. And with only 5 stars, you get something like 20% of the sky background. So 20% of the diffuse galactic light that I see over the entire sky comes from only 5 stars. Light from these stars, now this is something that's very difficult for people in other areas of astronomy to understand. The light from these stars, the sky is optically thick. And so in the ultraviolet, the sky is optically thick. That means that light doesn't penetrate very far into the galaxy. And so when you look at the sky, you actually only see out about 200 or 300 parsecs. That's about 600 or 700 light years. So when I look at the sky background in the ultraviolet, I actually only see out about 700 light years, maybe 600 light years. This is different from other areas. If I look at the infrared, this optical depth of the dust is almost transparent at infrared, at gamma rays. So if I look in the infrared, I'll see all the way through the galaxy out to the extragalactic light. Same thing in the gamma rays. I look all the way through the galaxy. But the UV is where the galaxy is the light penetrates the least. So I see the least distance into the ultraviolet. So now I look at this and I create different models. And this is the way it always works in astronomy. The bottom right corner here is the actual data, and with the positions of the bright stars. And so what I have to do is I have to compare my models with my data and see what gives me the best fit. So is it this one, or is it this one, or is this one, or this one? And I use various parameters. I try different things out. And when I get something that fits well, then I say, okay, well, that must measure reality in some way. But it may not be unique. When you're doing astronomy, the problem is that you're never actually, you can't change the conditions of your experiment. And this may be a good thing. We can't increase the temperature of the sun by 100 degrees just to see what would happen. Rather, you take the sun and you say, okay, I know the temperature of the sun and it looks this way. So now I try to model that. And then I look at another star and I say, okay, well, this star looks hotter than the sun, so I have to use a different model. And I put everything together and I try to get some unifying model. And this is always true in astronomy. Everything is model dependent. More than any other field of science, you have only data. Everything rests on data. You try to get as much out of the data as you can, but finally everything is limited by the data that you get. All right, so I get various models for the data, and I can observe some broad trends. So you remember I told you that that whenever you look at anything with the galaxy, you will always get things that are brighter towards the galactic plane. And so that is true of the sky background also. As I look towards the galactic plane, it's of course brighter it's always brighter as I get closer to the galactic plane. And because you're looking through increasing thicknesses of the galaxy, anything that's actually related to the galaxy should form a cosecant plot. And so you see that quite nicely here. That's 1 over cosine. So in both the FUV and the NUV, you see that the data, these shaded regions here, are very nicely fit by this cosecant plot. If I go down to the to shortward of 900 angstroms, no longer is that true. It's still, you can see this remnant of this cosecant plot, but you do get very faint regions even near the center of our galaxy. Now, the reason for this is because the dust is so optically thick as you get down to that you only see out, you don't even see out the 500 or 600 parsecs that you might see at the longer wavelengths. You might only see 200 parsecs. And so there, you only see very local effects. You won't see any of these big galactic trends. Instead, you only see local effects. Now, as I told you, when you look out towards the poles, the light from the galactic contribution is minimized. There's not very many stars out there, and there's not very much dust there. So the diffuse galactic light is minimized. And so when I look out at the poles, what I can hope to see is this extragalactic light. And so here are two images of the north galactic pole of the galaxy. If I look at the south galactic pole, it'll differ in detail, but the general properties will be the same. And so here's the FUV and the NUV, and here's the infrared. Now, if I look at the infrared emission, what is the infrared emission? It's emission from the dust. It's thermal emission from the dust. So in the ultraviolet, the dust absorbs photons from stars, typically ultraviolet photons, and those photons heat the dust grains, and these dust grains re-radiate at temperatures of 20 to 30 Kelvin, and they re-radiate in the infrared. So when I look in the infrared here, this is at 100 microns, I will see the same dust here that I'm seeing in scattering in the UV, but I'll see it in emission in the infrared. And so you can see these broad trends where you see the IR in the FUV. But oddly, I don't see that in the NUV. If it were actually dust emission, I would have expected to see these, whatever I see in the FUV, I would have expected to see in the NUV also, but I don't. So why is that? Well, what our belief is that most of what we see here is not actually dust emission, but rather is emission from molecular hydrogen fluorescence. Now, when you have these molecular clouds, you don't get molecular hydrogen in the general interstellar medium because there's too many ultraviolet photons, so it dissociates the molecular hydrogen. But when you look in areas like these molecular clouds, not the very big, dense molecular clouds that you might see in the plane of the galaxy, things like the Orion Molecular Cloud or the Eagle Nebula, these are thin, wispy things, but nevertheless, they have enough molecular hydrogen that you see that molecular hydrogen in the FUV. This is the fluorescent bands of the molecular hydrogen, but you don't see it in the NUV. And that's right. You don't see this hydrogen fluorescence in the NUV. So again, this goes back to what I was saying about everything in astronomy being model dependent. You have to get a picture. You come in with some preconceived notions, and then you look at it and something fits. So when I first saw this, I said, oh, okay, look, I see these dust bands in the FUV also. And so what I must be seeing is scattering from the dust. But then I looked at the NUV and I don't see this. So now so that maybe that's not true. So what else could it be? Well, molecular hydrogen. So you put these different things together, and hopefully finally everything makes sense, or at least makes enough sense for you to convince the referee. And so now when we look at this galactic, at the galactic poles, what we see is that we break it up into the different components. And so here, the blue line here is what I think the diffuse galactic light is. The green line is what the extragalactic light is. And the two of them put together don't actually fit what I see. So here, there's actually an offset between my observations and what the model tells me. The model tells me that there may be 100 of my photon units, photons per centimeter squared, per second per steradian, per angstrom per steradian. But really, I observe about 300. So that tells me that there's about 200 units that I just don't understand. It's about 200 of these photon units that I can't explain with what I see. And what is that? Well, it must be a contribution from the extragalactic background or the galactic sky background that we don't understand. Now, there's a joke in astronomy that whenever you have anything you don't understand, you say it's dark matter. So we postulate that this 200 units or so is from dark matter. Of course, we have no reason to say so. It's just 200 units that we don't understand. Now, as I told you, the diffuse sky background extends all the way from the UV out to the infrared, or actually from gamma rays out to the radio. And so I thought I would just say a few things, spend a couple of minutes on the diffuse optical background. What I've talked about is the diffuse ultraviolet background. Now, the diffuse optical background is this region between 300 nanometers and about 900 nanometers. The problem you have is the sun. The sun is bright, and anytime you're within the solar system, you observe nothing but interplanetary light. You observe zodiacal light. So they've tried to observe the extragalactic background from the surface of the Earth, and the way you do that is you do subtraction. You look at some field and you look right off that field. But it's very difficult to do, and none of the data are very trustworthy. So what we would really like to do is to observe from out of the solar system. And so going out of the solar system is, of course, difficult. The only spacecraft that have gone out are the two Voyager spacecraft and the Pioneer spacecraft. And now New Horizons has gone out to the Kuiper Belt, but just not many observations. But when we do take these observations, what we find is that the contribution of our solar system decreases considerably. So these are from Voyager and New Horizons data, and so as I go further and further away from the sun, I get less and less contribution from the solar system. And this is true in the optical also. And so here, what I show is Pioneer data from outside of the solar system. So these are the only observations from out of the solar system in the optical. And they're just not very good, because Pioneer, it's an old instrument. The instrument was not very good, and it was never intended to observe the sky background. But still, we managed to get some data. So what we would ideally like to do is to send a payload or send a spacecraft. We're trying to use New Horizons data. We do have some good New Horizons data. But again, New Horizons is not optimized for this. What we would really like to do is to send a small spacecraft out, put some optical and UV imagers on board and spectrographs on board, and just send it out of the solar system. And with that, we think that we can really make a good contribution to observing the sky background. And what we would do is that these are the observations of the extragalactic sky background, the cosmic background, in different wavelength bands. And so here you have the quite well resolved, quite well understood radio background, the cosmic microwave background, the infrared background, and the X-ray and the gamma ray background. And these are well understood because the galaxy is more or less understood at these wavelengths. It's more or less transparent, and you can see out of the galaxy. And even in the infrared, where the galaxy is a strong contributor, you can do a pretty good job of observing the galaxy. What we don't have a good sense of is this region between the cosmic optical background and the cosmic ultraviolet background. And so this is where, again, we think that if we could send a spacecraft out to outside of the solar system, it would do really wonderful stuff. We have a couple of opportunities where we do have things that we can use, or things that hopefully we can use soon. And one is New Horizons. We do have some New Horizons data, and we are trying to use it. And as I said, it's not optimized for observations of the sky background. It's optimized for observations of Pluto. But nevertheless, we've been able to use it to get some good good numbers. If we could put an imager on the moon, a far ultraviolet imager on the moon, that would do wonderful science. The reason is because we would be outside of the Earth's atmosphere. If we're outside of the Earth's atmosphere, we don't have to worry about any of these terrestrial lines. If we look between about 130 nanometers and about 180 nanometers, that is an instrument with a cesium rubidium photocathode, we wouldn't see any contribution from solar system light. All we would see is galactic and extragalactic light. So if we could put an imager on the moon, near side, far side, it doesn't matter to us. If we could put an imager on the moon, we could make some really groundbreaking studies of the ultraviolet background, which would feed into all of these models of the complete sky background. And as I mentioned at the beginning of the talk, we do have a spectrograph that will go on the Chinese Modular Space Station. This was part of United Nations Office of Outer Space Affairs, UNOSA program, where the Chinese opened up some 20 slots on the space station. And we put in a proposal and we won one of those slots. So in about 2022 or so, probably late 2022, early 2023, we will have an instrument on the Chinese space station that will hopefully take observations of the diffuse sky background. So let me end here, and I'm happy to take any questions. Let me say one thing before you go on. Based on what you said, one of the things I wanted to stress here is that, again, these data and much other of the data in astronomy is available. And so people can download the data and they can play around with it. No matter what field, if you're in computer science, if you're in astronomy, if you're just interested in looking at pictures of the sky, just get the data and see what you can do with it. Yeah, sorry, I didn't mean to interrupt you. Well, it's there is a correlation, but the thing is that when you're looking at neutral hydrogen, what you're looking at is you're looking at the gas, but the neutral hydrogen you see much deeper than you do in the ultraviolet. So as I said, I look out about 600 parsecs. When I look out at the neutral hydrogen, I will look all the way out through the other side of the galaxy. And so it's correlated up to some point. When I don't have much neutral hydrogen, then as I add more neutral hydrogen, I'll increase my UV background. But eventually it'll saturate. I keep adding neutral hydrogen, but I'm saturated because the optical depth, how deep I can see in the UV, is limited. So it plateaus. It starts out linear and then it plateaus. No, this is always the question. Our model can never represent reality completely. And there's a beautiful quote from Isaac Asimov. If you're, what is it? Oh, I can't remember. Anyway, paraphrasing, it's that if you don't understand your data, then the universe doesn't care. The universe is right. Your models are what's wrong. And so how do you understand, is it a complexity in my dust scattering? Am I seeing different dust at the poles than I'm seeing at the galaxy? I don't know. So I try different things. And finally, I tried to, you use Occam's razor. You use whatever you think is the best answer. But this is true no matter where in astronomy you look. And that's something that I think is important for students to understand. You read papers in which everything is beautifully laid out. But finally, you start to look at the assumptions and you say, okay, well, they're very persuasive there, but are they really certain that the universe is exactly 13.4 billion years old? What happens if the universe is 13.7 billion years old? So that's all I can say. It could be something else. I just don't understand what it is yet. I hope that answered the question. Oh, you see, that's a very interesting problem and a very interesting question, and it's a real problem, and it's again made worse by the sociology of science in general. So it used to be there's several things that go into this. Firstly, it used to be that you could just present results. So I would look at a star and I would say that star varies like this. And that would be a good result, and I could publish that. Now, for whatever reason, that is not sufficient anymore. You can't just say my star varies like this. Now you have to give some explanation for that. And so that's what I'm talking about astronomy and astrophysics merging together. But the problem is that and you must have seen this in other fields too. It's a big problem in medicine. No one wants to have negative results. So sometimes I do things and I have a negative result, but I can't publish it. And maybe I don't understand it, maybe, or I have a result that confirms something else. Again, it's not publishable. So how do I balance all of these together? And so when you say that becoming more interdisciplinary, I have a fear that it's actually becoming worse. It's becoming less interdisciplinary. You see, there's no way I can keep up with all of astronomical literature. Even over my scientific career, the number of papers published, the number of sheer pages published has gone up exponentially. It used to be that I could reasonably read everything in astronomy when I was a student. Now I can't do that anymore. There's just not enough time. And are we becoming too narrow? It is a significant question, a significant problem. The other thing that's happening is that we're getting overwhelmed with data. Even in my own project, I was dealing with 2 terabytes of data and something like 70 million lines of individual data points, 70 million data points. Even there, it takes I don't know, maybe I've forgotten, maybe a couple of weeks to run through the data. So, and there's no way I can check every single point. And it's gotten so bad that in fields like high energy physics, where they get petabytes of data or more, zettabytes of data or whatever they call them, they even throw away data. So they have to pre-process their data with a model. And things that don't fit the model get thrown out, which is going to be true of some of the new astronomy experiments. So I worry that somewhere along all of this, we're going to be losing important results just because we're going to be so overwhelmed with data and we have so few people that we just can't possibly do everything in the detail is needed. Again, I hope I answered the question. It's not a problem. I'm not going anywhere. No, because you're troubled by the ozone layer. I mean, it's great for us, right? Because we don't get skin cancer, but the ozone layer will absorb all ultraviolet radiation. So we can't even see out of the atmosphere. We have to go to at least 250, 300 kilometers. Oh, no, I don't think so at all, because everything tells you different aspects. So again, this is what I was trying to convey, that we all study, you see, I'm an ultraviolet astronomer. And the reason I'm an ultraviolet astronomer is because I've worked in ultraviolet astronomy all my life. And that's because it tells you something that you can't get in other fields. I mean, I can go on about why it's important, but this is true of every area of astronomy. Every area of astronomy will tell you something that no other area can observe. And this includes things like this neutrino observatories, of gravitational wave observatories, all the non-EM stuff. They give you information about the universe. And so what we do is we take all of this information, all of these different fields, and we try to put it together into a... And this goes back to that previous question. Do we need interdisciplinary work? Yes, absolutely, we need that interdisciplinary work to look at UV astronomy and radio astronomy and gravitational wave astronomy and make everything fit together. But that's difficult. Basically mathematics. You talk mathematics in one sense or another. So that's where, I mean, of course, this is an ideal, right? We all know that there's national interests. When the South African boycott was there for apartheid, I actually supported it. I mean, it's a complex reality. But the goal is that we do have an international community. And something like COSPAR, the Committee on Outer Space Affairs? Anyway, whatever it is, COSPAR. They worked throughout the Cold War. And the goal was always that regardless of political fighting, the scientists would work together. So how that works in reality, I mean, difficult. You get a little bit of my personal philosophy there. Let me say one more thing there. And this, all this fighting in the dark, I mean, I don't understand it. I don't understand what the reason is. But what I wish they would do is, we have our observatory there at Hanley. And the Chinese have an observatory. They're building an observatory on their side of the line. We're building a solar observatory at Merak on Pangong Lake. I wish we would just take that whole area and dedicate it to astronomy, an astronomy open area. Unrealistic, right? Well, the ultraviolet background is more a consequence. When you have galaxies form, you have stars, you have young stars, you have they give rise to this background, and so it's not so much that they cause something, but rather they're a diagnostic of galaxy evolution. So by studying the UV background or any sky background, you understand the processes that gave rise to that background. It's very faint, so it doesn't really affect much. What I do is I take a model of the dust, and so let me go back to that picture here. I have it. I skipped over it. Yeah. So I take a model of the dust, and what this is a 3D model. So it tells me where the dust is. The problem is that it's not very precise, because what I'm doing is I'm not measuring the actual dust. What I'm doing is I'm actually measuring the extinction to stars. So I have so many stars here, so many stars here, so many stars here, and I'm measuring how much dust I see in the line of sight to the stars, because dust only blocks light. It doesn't give light. So, so based on that, I get this 3D distribution. And then I divide it up amongst the boxes in my galaxy. So you can see that I'm limited. In an ideal world, I would have a much finer grid. In reality, what I do is I have a grid of I have 5 parsec size boxes, 15 light year boxes. If I had more data, I might have used 1 parsec boxes. But that's all I do. I just take each box and I say, okay, there's so much dust in that box. Then, in order to calculate the scattering that I see, I take a photon from the star. I figure out what direction it's moving, picking random numbers, and then I say, okay, that photon goes through 1 box. Is it absorbed? No? Okay, go on to the next box. Is it absorbed? No? Go on to the next box. Is it absorbed? Yes. Okay, re-emit it in some other direction and send some radiation back towards my detector. Okay, I hope that was explanatory. My programs are all available, so you can download them and take a look. They're all written in C, NCC, so you can freely available.
Now we have the last question. Why do we see very less UV photons before? Are there more UV photons in the galaxy?
Oh, absolutely. There's so much hydrogen. See, what happens is that hydrogen, there's so much hydrogen there that every UV photon will interact with the hydrogen atom. So you get the UV photon comes in, it hits a hydrogen atom, and it's absorbed. And then that hydrogen atom will re-emit a photon in some random direction, which means it's lost to you. And it goes back to its ground state. And then it can absorb another UV photon. So there's so many hydrogen atoms out there that UV light just cannot get through. And the distance is surprisingly short. It's like maybe about 10, 15 light years, 10 light years, that's it. So only the nearest stars.
Yeah, so I guess
Okay, thank you. Very good thing that you're doing here, keeping active. Yeah. Okay, bye.